It is a great honor to contribute to celebration of Edmund Becquerel 200th anniversary meeting. My name is Takahiro Wada of Ryokoku University, Japan. Today, I'm going to talk about development of CIS solar cells from perspective of materials scientist. I entered the field of photovoltaic science with the development of CIS solar cells in 1991. I served as a project leader of high-efficiency CIS solar cell research at Matsushita Electric Panasonic Corporation. The project was supported by the NIDO as a part of new Sunshine program conducted under MITI Japan. This is the efficiency of CIS solar cells and key technologies. The history of CIS solar cells began in 1975, when Bell Lab achieved 12% efficiency with the junction of CDS and CIS single crystals. In 1976, the University of Maine fabricated thin film CIS solar cell with 5% efficiency. In 1980s, Boeing and Alco demonstrated CIS solar cell with more than 10% efficiency. This is phase diagram of copper to selenium, indium to selenium-3 pseudo-binary system. Chalcopyrite copper indium diselenide, tau-3, transformed copper indium to selenium-3, tau-4, and copper indium 5 selenium-8 with increasing in indium to selenium-3 ratio. Becquerel invested so-called three-stage process. The process provided the basis for 20% efficiency. Indium, gallium, selenium were co-evaporated to form precursor film of indium to selenium-3 phase. The precursor was then converted to chalcopyrite copper indium gallium diselenide by exposure to flux of copper and selenium. The final film was smooth surface with tightly packed grain and had graded gallium content as a function of film depth. They achieved 15.9%. After that, we prepared device quality CIGS film by three-stage process with a composition monitor. The chemical composition of CIGS thin films was monitored in real time during the physical vapor deposition. This is the variation of beam flux, substrate temperature, and GGI ratio of the film. The film temperature is almost constant at around 550 degrees C. At that time, GGI ratio is lower than 1. The film temperature decreases with increasing GGI ratio, and film temperature increase, decreasing GGI ratio. The temperature of growing CIGS field depends on GGI ratio. The system is very useful, easily applied to composition control of CIGS film deposited by the three-stage process. We could fabricate high-efficiency CIGS solar cell by three-stage process and composition monitor. In 1997, we achieved 17.6% efficiency. the high efficiency CIGS solar cells could be fabricated with good reproducibility. Euro-CIS group proposed new heterojunction model. In 1993, University Stuttgart group, Professor Schock group found kappa deficient layer at the surface of indium-rich CIS film. They proposed that the kappa deficient layer played an important role for CDS-CIS heterojunction solar cells. We determined the crystal structure of kappa poor phase. Kappa indium-3 selenium-5 CIS-135 has the Stannite type structure with the space group I4-2M. CIS-135 is neither defect chalcopyrite with the space group IN4-2D nor ordered vacancy compound. In 2004, Paskowitz Polish group proposed the defined crystal structure of Stannite type CIS-135. In 2011, we confirmed the CIS-135 has Stannite type structure by X-ray absorption fine structure. In early 2000s, kappa deficient layer was found at the grain boundary of CIGS film by United States group. Their experimental result confirmed the theoretical prediction. Polar grain boundary interfaces are stabilized by massive removal of kappa atoms, leading to valence band offset between grain boundary and grain interior. That repels hole from grain boundary, thus likely reducing grain boundary electron-hole recombination, improving photovoltaic device operation. We determined energy level of valence band maximum and conduction band minimum of chalcopyrite fell and Stannite phase. Energy level of valence band maximum of Stannite phase is lower than that of chalcopyrite phase. The energy level of valence band maximum of chalcopyrite and Stannite phase decrease with increasing indium-2 selenium-3 content. In 2015, Tokyo Institute of Technology Group, Professor Yamada Group inserted kappa indium gallium-3 selenium-5 kappa poor CIGS layer at CDS-CIGS interface and obtained high efficiency CIS solar cells. Recently, some research group achieved efficiency of over 20% alkaline fluoride post-deposition treatment. Some group also reported that after alkaline fluoride post-deposition treatment, kappa deficient layer was formed at the surface of CIGS film. Solar Frontier achieved high efficiency of 23.35% by using kappa indium gallium sulfur selenium absorber layer. Stannite phase is unstable in kappa indium 3 sulfur selenium system. Crystal structure changed from tetragonal Stannite type kappa indium 3 selenium 5 to cubic spinel type kappa indium 5 sulfur 8 through the mixed phase. The region of single phase Stannite type kappa indium 3 sulfur selenium solid solution considerably narrow. The behavior is mainly due to instability of indium to be stabilized in tetrahedral sulfide environment with copper vacancy. Solar Frontier fabricated CIG sulfur selenium absorber layer by selenization of copper, gallium, and indium stacked layers and post-sulfurization process. Sulfurization after selenization, SAS process. A low temperature selenization and high temperature sulfurization. We made three-dimensional map of energy level of valence band maximum and conduction band minimum of copper, indium, sulfur, selenium system. The VBM level of CIGS selenium system does not change significantly with increasing gallium content. On the other hand, the VBM level of CIGS selenium system becomes deeper with increasing sulfur content. This is the schematic depth profile of the level of valence band maximum and conduction band minimum in the CIGS selenium absorber layer by controlling GGI sulfur plus selenium ratios. This is popular band profile. A sulfur-rich surface layer lowers valence band maximum level at the front interface, and it acts as the hole blocking layer for reducing electron hole recombination at the front interface. We also fabricated this profile by post-indium sulfur aqueous solution treatment of CIG selenium surface. This is the schematic microstructure of CIGS selenium absorber for high efficiency CIGS solar cells. When selenium in CIGS was replaced by sulfur, the valence band maximum decreases and conduction band increases. Therefore, grain boundary of CIGS layer with high sulfur concentration have lower valence band maximum and higher conduction band minimum. A selen-rich grain boundary has lower valence band maximum level. It acts as a hole blocking layer for reducing electron hole recombination, similar to a kappa poor phase. I hope that we can achieve more than 55% efficiency in near future by controlling bulk and interface properties in CIGS solar cells with a novel device structure. I acknowledge Japanese collaborators and international members of CIS community, Japanese CIS Consortium and MRS Spring Meeting members and EMRS Spring Meet members and ICTMC members. And this is Professor Shock's group and recent group. This is my CIS power plant. My CIS power plant has started operation since March 13th, 2018. This solar power plant has generated 155,000 kilowatt-hours of electricity. Thank you for your attention.